Well then, next we would like to move on to the second theme, and the next presentation is R&D and NTT Research Inc. Dr. Yamamoto is going to talk about the quantum neural network. So, Dr. Yamamoto, the floor is yours.
NTT.
Thank you very much. I'm the director of NTT Physics and Informatics Laboratories. Yamamoto is my name. Today, I would like to share with you a new type of computer, a quantum neural network, which NTT is developing. The basic objective is to connect quantum and brain with optics. We want to combine these two different functions through optics. Now, this machine is a machine back in 2014. It started with a small machine that has 4 neurons into a synapse. But in 2016, we're able to connect 2K neurons with 4 million synapses. We're able to develop mid-size machines. In 2019, we were able to have a prototype of this mid-size machines. It is only at a test phase, but we believe that 100,000 neurons and 10 billion synapses can be combined. So we have already begun or completed development to this phase. So today, I would like to talk about what type of problems can be solved with this quantum neural network. That's what I would like to start my presentation. So there is the combinatorial optimization problems. This is ubiquitous in various places throughout our society. One example is on this page. Is the lead optimization for discovery of small molecule drug, peptide drug, and biocatalyst. Let me cite another example. That will be the resource optimization in wireless communications, logistics, and scheduling, or real-time resource optimization would be the other example of problems. Another example is the compressed sensing or sparse coding for astronomy, as well as magnetic resonance imaging and MRI and computed tomography or CT. And it's a new mathematical methodologies. And the last example would involve self-driving cars, healthcare, and voice and image recognition, the so-called deep machine learning that are used in these areas. This is one of the bottlenecks because because this requires a very large amount of calculation. So we believe that quantum neural network can solve these problems. So let me explain what lead optimization is. Allow me to elaborate a little bit on what exactly this is. A drug discovery can take a very long time, between 10 to 15 years or 20 years. And the first step of the drug discovery is to identify a group of compounds that are attached most stably to target protein that is responsible for a disease. So if these proteins, if we're able to identify these small molecule drugs, then we're able to identify a group of compounds that attach most stably to target protein, then we can address these diseases. Now the search space is 10 to the 14 compounds. These are the candidates for compounds. And we have to identify 100 or 1,000 candidates out of these search space. That is what we have to do. This is described as the lead optimization. Now, on the other hand, in the case of biocatalyst discovery, we have to find a number of candidate compounds. The first step is to identify a group of proteins that capture most stably a target compound that is useful for a certain chemical reaction. And the search space would be enormous, 10 to the 690th. And from these proteins, we have to select anywhere from 10 to 1,000 candidate proteins. That is the job of the lead optimization. So, how enormous is this search space? You have to remember that the number of atoms in the observable universe is only 10 to the 80th. So I think this will give you an idea as to how enormous the search space involved is. So by using quantum neural network, it means that with 4,000 neurons or 60,000 neurons, you're able to realize lead optimization. You're able to implement lead optimization if you have the quantum neural network. Now, on the bottom of this page, we tried to capture this. We're able to confirm this through numbers. So this is the result of the small molecule drug test. On the bottom, you'll find the brute force search, where all sorts of candidates have been exhausted. But we are interested in these small compounds with very low level of energy. So in order to identify low energy compounds, then ordinarily you would actually have to utilize theoretical Boltzmann distribution as a filter, and then you're able to reach a answer. So through this brute force search using the most various computers, this is the number that you're able to reach. But then through quantum neural network, through sampling, you're able to arrive at the exact direct response that you want. So this is the effect of the quantum neural network. Next, I would like to talk about compressed sensing. In terms of astronomy observation or medical imaging, original data described by n-dimensional vectors are converted to m-dimensional observation data via scattering matrix. But ordinarily, this m-dimensional observed data is much smaller than the original dimension n. So even if you have the scattering matrix, even if you have an accurate understanding of the scattering matrix, we cannot construct the original data from the observation data. So be it astronomy observation or be it medical imaging, we see a very serious problem of the degrading of the picture quality. But then what we're interested in is this. What is, the object of our interest is actually sparse data in most cases. So as you see, so in the case of astronomy observation or medical imaging, in those cases, the most elements of the original data vectors do not carry any useful information at all. So we have a universal character of self-organized objects, such as the universe and human body. In other words, the useful data information is contained in only only very small part. So in the case of sparse coding, we have to identify non-zero components for support estimate. We have to iterate the inverse metric computation. By doing that, by iterating that, we're able to resurrect to the original data with a great deal of accuracy. This is referred to as the compressed sensing or sparse coding. Now, the bottom panel shows the theoretical limit of recovery efficiency by exact sparse coding method. But if you use modern computer, and if you want to do compressed sensing with computers, you have to go through enormous calculation. So therefore, you have to use approximate method. So at this moment, you cannot reach the optimal resolution. So what we're showing you is that quantum neural network can achieve the theoretical limit. We can achieve the theoretical limit and identify non-zero compounds and also address deep compressed sensing. Then let me now switch gears a little bit and talk about quantum computing per se. Is quantum computing a dream or a nightmare? Even among the scientist community, the views are divided. Is it a dream or a nightmare? So it was back in 1985 that Dr. David Deutsch of Oxford University who first presented this paper back in 1985. So the classical computers that we are very familiar with, the gate voltage in these classical computers is either 0 voltage or 1 voltage. And on the other hand, the quantum memory in quantum computer is simultaneous 0 state and 1 state in one state. And this is referred to as the quantum bit, which means that if you have n qubit information from 0, 1 to 1, 1 state, from state 1 or state 2, you can do this with n qubit system. In the case of classical n bit, you can only show one state. So therefore, be it in the case of modern computer and classical computers, if you try to address the issue of the combinatorial optimization, you have to compute the cost function one by one for to the n different inputs. And this to be done in a sequential fashion. And then you're able to reach the optimal optimization. In the case of QNN, though, you're able to do this. You're able to do this simultaneously, which means that you can compute cost at the same time, and you're able to incorporate this into the n input states. So therefore, you're able to arrive to the optimal conclusion. So if the wave function can be extrapolated into the classical computer, then in just one calculation, without going through the 2 to the n calculation, you're able to reach the optimal conclusion. Now, fortunately, this wavelength, this quantum wave function, based on which we're able to reach the optimal solution, if we try to take this out of the classical computer, is not possible aside from exceptions. And that, I believe, is the weakness of the quantum computing. And as you see on this page, 2 to the n, all the candidates that are 2 to the n, so we have the solution candidates. We are to reach at one optimal solution. What must be done to draw out this one single optimal solution? So you have the root. So you have the root n. You have to amplify that to 1, and then in all the you have to you have to attenuate that to 0. So increase and the attenuation of the amplitude. In 1997, Grover has discovered that. So Grover algorithm root, if you repeat this 2 to the n square times, then you will have completed the required preparation for the calculation. But then, as you see, root 2 to the n, the calculation time is exponential. Now, on the right-hand side, you see the combinatorial optimization problem. and have time to solution by an ideal quantum computer for the combinatorial optimization problem can be achieved. So what will happen when you have the ideal quantum computer? What will happen when you expand the problem size? What will happen to time solutions? The time to the solutions, if you have the ideal quantum computer, it can be as long as 200 years to 20 billion years. However, we are interested in several thousand bits, or that is the number of bits that we're interested in. So therefore, this would not represent a solution considering the problem size and bits required. So if you have the quantum computer developed, then all these difficult problems can be solved in one moment. You see that type of newspaper reports. However, that is a typical fake news because that simply is not possible. Then at NTT, in order to solve this problem, we want to try a fundamentally different approach in order to address this issue. And that is what we have been addressing. So this is what I would like to talk about now.
So, well, QNN quantum neural network is the approach we would like to take. And this particular computer, in two aspects, is different from the quantum computer. For one thing, quantum and classic features are being combined together, and these are to be looked for the computation device. And artificial atomic would be just be operated at 10 millikelvin, very low temperature. And then this is really like a superconducting circuit. And it is for digital quantum. And in case of the QNN optical parametric oscillator, and it can be operated at the room temperature. And if below the threshold, this is the quantum analog. But if it goes above the threshold, and this would change into the classical digital device. And by using these devices and QNN, and it will start the computation as the quantum computing, but completes the computation as the classic computer. And the major difference and global and parallel computation can be achieved. And in case of the quantum computing, it will be done local and equation computation, and then there would be just having this series of one bit. In case of the QNN quantum neural network, and it will be the coherent wavelength spreads in its entire network, and for each of the neurons, and simultaneous computation can be done. And so this is the mechanism with respect to QNN. And next, why are we not just looking for the quantum computation research, but need classical computation research as well? And I'd like to explain the reasons why. In 2008, the Nobel Physics Prize winner and Professor Yoichiro Nambu came up with the concept of spontaneous symmetry breaking. And then if you would just leave your hand off the pencil standing on the table, and it would just fall down. And this is a very natural phenomenon. But this is exactly is this spontaneous symmetry breaking. And in the world, in this classical world, this is the phenomena taken for granted, but not in quantum universe. And this is just applicable in a classic world. And then irreversible decision-making process, and then this solution will be selected in an irreversible manner by the machine, and then machine will have the amplification of the exponential the amplitudes. And in case of the quantum neural network, and then you have all these the quantum correlation developed by the parametric oscillators, and then you have a certain rule, and for the collectively the OPOs would have the breaking of the symmetry, and then they would go for the selection. And the optimal solution, when it is selected, and the amplitude of that below the threshold, and it will be amplified exponentially and go to 1. And the time needed for that is just about the time interval of a photon lifetime. And so exponentially, explosion time is not really required. And that is one of the features of this particular machine. And the next slide shows what is being developed. And three experimental quantum machines and time to solutions are compared, and the results are shown. And what I have just described, and in terms of the problem size and theoretical quantum computing and time to solution, are shown here. And in case of quantum neural network, and what was really developed by the Rigetti quantum computer, and also the quantum annealing machine developed by D-Wave 2000. And vis-a-vis all these the two machines, QNN would achieve much more higher instead of the speed and 10 to the 7th power. And so if you compare to the theoretical quantum computing, and it is by 10 to the power of 19th difference. Now, let me switch a gear a little bit, and I'd like to really talk about the history of QC research at NTT laboratories in the last 40 years. And all these constituent optical techniques were used for the QNN, like for homodine detection and for the stabilization of optical fiber resonators. Coherent optical communications research, which was started in 1979, really resulted in these findings. And in 1986, in QNN, and the very key device, the method or the concept of the measurement-induced control of a quantum state of light was experimentally demonstrated, and that principle was to be applied for the OPO, and that was really released and announced in 1988, and this proposal was really released, and then this was really achieved by the differential phase shift quantum communication, and it was really demonstrated by the squeezed vacuum state pulses from PPL and OPO, and it took 7 years until we have been able to really demonstrate that. And then the differential phase shift quantum communication protocol was proposed in 2002, and then the demonstration test was conducted in the next 10 years, and in 2014, as I have just said, in QNN, the very first experimental machine was developed, and by using that, the problem was solved. And in 2016, scalable the quantum neural network based upon the measurement feedback system, it was demonstrated and coming into this year. And vis-a-vis the quantum computing and quantum annealing, we were able to really benchmark our machines. So that is the sort of the history of the development. Now, looking into the next 40 years, which direction will NTT laboratories will move in? And this is summarized on this slide. And on our part, the quantum science and brain science, and then we believe that there exists a new frontier in this interdisciplinary field between those, and then the new principle, which would be really playing a great role in the next generation. The quantum neural network is there, and so in order to fuse the entirely different fields and to just apply it in a practical application, and the technology of the optical communication technology are going to be really used. And I think, that's how the future computing would be developed. And in this kind of interdisciplinary field, and a world-class, leading, experimental or the laboratory system needs to be established. And so we really have to establish the open, on the research, institutions going across the industry, laboratories, and academic institutions, and hardware, software, and the new principles. And we do have the NTT Basic Research Lab and NTT Software Innovation Center and Phi Lab of NTT will be responsible for each individual fields. And as the partners to the NTT R&D, 8 research institutes partnering in Stanford University, Caltech, and Cornell University, and MIT, and also the NASA Ames Research Center, and also One Qubit and Swinburne University of Technology and University of Michigan. And these partner institutions are going to work together with us. And lastly, as for the future research themes, I'd just like to say a few words. And already, the very first theme is a human brain is already a quantum computer, and this might sound a ridiculous question. But in the last 10 years, neuroscience areas and what has been discussed very actively includes and this functional MRI can really observe the correlation length of the brain at rest. And just like QNN and aging network will have this very similar spin-to-spin correlation. And at the phase transition point. In this way, and the oscillation thresholds of the QNN and also the human brain at rest. And all these features or characteristics shown in the assumed state. For one thing, and it will have a very broad distribution number correlation length, and then randomness is maximum, and also responsivity is for maximum. And whether a human brain is already a quantum computer or not, and then at this kind of bias point, and then you have the sort of the largest communication capacity and the largest maximum information storage, and also the amplified signals. And in 2015, in Physical Review Letters and editorial, already has focused on this point, and this kind of message was sent out. And in the 21st century, all these the contribution made by the physicist is discovery of the measurement methods or the new principles related to the measurement in the 20th century. But what can be the contribution to be made by the physicists in the 21st century, and how large number of neurons collectively interact to produce emergent properties like cognition and consciousness or decision making, and this kind of very high level and sophisticated information processing the technology can be achieved, and this would be the largest mission to be really fulfilled by the physicists. And we at NTT perfectly agree with this idea, and I think this is the direction we should really pursue. And this is the very last slide that I'd like to share with you. And as I said, three the quantum machines and how they are going to be scaled up. And the left-hand side, which shows the number of neurons or number of qubits and how it has been increased. And on the right-hand side, number of synapses and how the spin-to-spin couplings number is increasing. And in case of the quantum annealing machine and the quantum computing and QNN, and the neurons would decide the problem size, and number of synapses would control the computational capability, and then where the human brain is located in terms of neurons, number of neurons, and 10 billion, and the synapses were 100 trillion synapses, and QNN and in terms of numbers, and 100,000, and then 10 billion of synapses. And so the difference is 4 digits as well as the 6 digits. And so if the trend is going to be progressing in this line, and by 2025, so in terms of the number of neurons and in terms of number of synapses, and the QN technology will become on par with that of the human brains. But that could be quite challenging to really realize that. And this concludes my presentation. Thank you for your attention.